So, very good morning. Welcome back, dear viewers. So, yesterday in module 6, we discussed on vapor pressure as well as compressibility, and we worked out a numerical problem on compressibility of fluid. We discussed the factors affecting compressibility and what is bulk modulus. So, bulk modulus is just the reciprocal of compressibility, and how the bulk modulus and compressibility for liquids and gases vary, we discussed. So, gases are highly compressible, whereas liquids are generally treated as incompressible. Under special circumstances, they can be considered compressible. The compressibility of liquid becomes important under special circumstances. Under ordinary circumstances, in most of the engineering problems we come across, liquids are generally incompressible and gases are highly compressible, and also they are highly expandable. So, now in this module today, module 7, we will discuss on surface tension and capillarity, the last property of the fluid properties we have been discussing. Now, we have studied about molecular attraction. We differentiated between the solids, liquids and gases in terms of the spacing of molecules and the intermolecular attraction. Now, this surface tension and capillarity is a characteristics of only liquids. Now, liquids, you have molecular attraction, you talk about molecular attraction. So, what are the properties possessed by the liquids due to molecular attraction? So, two properties are of interest. One is called cohesion. One is called cohesion and the other one is called adhesion. Now, what is cohesion? Cohesion is the intermolecular attraction, that is attraction between molecules of the same liquid. Say for example, in philosophical terms, if you want to put it, how much you love yourself. So, how? See the love I have for me, within me. So, how much I love me. So, that is the attraction between molecules of the same liquid. Now, what is adhesion? So, adhesion is the attraction between molecules of a liquid and the molecules of a solid surface with which the liquid comes in contact. So, for example, again in philosophical terms, to understand adhesion, say the attraction a man has got for the other gender, say the male has got for the other gender female, or female has got for the other gender, the biological attraction. So, here the attraction which the liquid molecules show for molecules of the solid surface with which it comes in contact. Say for example, you are storing water in a container, say for example a plastic bottle, and then you are storing water in a metal container, and when you are removing the contents, the liquid contents from the container, that is you are making the plastic bottle or the metal bottle empty. Now, if you see, there will be liquid particles, water particles sticking on to the wall of the inner surface of the wall of both the containers. Now, in fact, in plastic bottle, the liquid molecules or the water molecules sticking on to the plastic surface will be less compared to the number of liquid water molecules sticking onto the metal surface. So, that means the adhesive property of water towards the metal surface is much more than the adhesive property of water towards a plastic surface. So, the attraction, what is the force of attraction or the quantum of attraction that prevails between molecules of a liquid and molecules of a foreign substance, that is a solid surface with which it comes in contact, that is called adhesion. Now, what is the characteristic possessed by a liquid because of the property of cohesion? So, this intermolecular attraction gives the ability to resist tensile stress. So it's very small quantity. This tensile stress, the magnitude of such tensile stress is very less. So what is the ability of the liquid to resist tensile stress? Because of the property of cohesion. So because of cohesion, the intermolecular attraction, the characteristic possessed by a liquid is that it has got the ability to resist tensile stress. And again, what is the characteristic possessed by a liquid because of the property of adhesion? So that is, the liquid has the characteristics of sticking to the surface of another body with which it comes in contact. This is adhesion. Okay. Now let us discuss in detail surface tension and then bring out the units, the dimensions, as well as the various illustrations involving surface tension. So let us consider a vessel containing a liquid, say an open vessel containing liquid, say water. So this is the free surface of water, free surface of water. Now this is water and this is atmosphere. Here you have got atmosphere, the overlying atmosphere. So let us consider a point A inside the liquid mass or the water mass. So if you take this molecule, the liquid molecule or the water molecule located at point A, now it is surrounded by water molecules in all sides. So this is attracted by fluid molecules or water molecules in all directions. So the force exerted or the molecular attraction exerted by a molecule located on the left of particulate A and the right of particle A, they will be nullified. Similarly, the force of attraction exerted by a molecule located on the top of the molecule at A and the molecule located at the bottom of the molecule at A, these two forces will balance with each other. So the net force will be 0. So the net downward force on each molecule. So what happens? So it is surrounded by other liquid molecules in all directions, so that the molecule is equally attracted on all sides, and hence the net force of attraction exerted by molecules surrounding the molecule at A is 0. So the net force of attraction on the molecule which is located inside the mass of the liquid anywhere is 0. Whereas let us consider a liquid molecule located at the free surface of the liquid, say water, say let this be point B. Let us consider a molecule located at a point B on the free surface. Now if you take the molecule at B, the water molecule at B, it is attracted by a molecule which is located below B. It is attracted. Whereas there is no molecule, water molecule above B to attract it. Therefore what happens? There is a net downward force. There is a net downward force on each molecule at free surface due to the force of attraction by molecule below it. So if you take any liquid molecule on the free surface, these molecules are subjected to a net downward force because of the lack of molecules above them to attract them, due to the force of attraction by molecule below it. So this net downward force, what is the direction? It acts normal or perpendicular to the liquid surface. So this acts perpendicular to the liquid surface. So due to the attraction of liquid molecules below the free surface of liquid, a film or special layer seems to form on the free surface of liquid which is in tension. So it is under tension. So the liquid film on the free surface is under a form of tension, a net downward pull. So this tension enables the liquid surface to support very small loads, say like a small needle, a metal needle. So this can be placed gently over the water surface, and this needle will be floating on the surface. It will not sink into the water, and it will be supported due to the tension of the water surface. So due to the tension under which the surface film is present. So how you can define surface tension? It can be explained as the property by which the liquid surface film, that is the film of liquid at the free surface, exerts a tension. It is under tension. It is denoted by the Greek symbol sigma. Sigma. So surface tension is defined as the force required to maintain unit length of the film at the free surface in equilibrium. So it is the force required. So tension is a form of force. So it is the force required to maintain unit length of the film at the free surface in equilibrium. So it has got units of Newton per meter. So force required, this is the force required is newtons to maintain unit length. So the unit length is in meters. So force required to maintain unit length of the film at the free surface in equilibrium is surface tension. So the SI units of sigma surface tension is Newton per meter. So again, if you can get the dimensions, if you want to use FLT system, it is F by L or F L power minus 1. If you want, you can have the MLT system also. You can express F in terms of MLT and then work out the dimensions. So let us now discuss the factors influencing surface tension. So surface tension is due to the cohesive force exerted by the molecules of liquid, that is intermolecular attraction. So surface tension is entirely due to cohesion, the intermolecular attraction. So what happens when the temperature of the liquid rises? Please note, surface tension is a property exhibited only of liquids. So when the temperature of a liquid rises, as we have discussed in viscosity, vapor pressure and compressibility, the molecular mobility increases when the temperature of the liquid rises. The cohesive forces get weakened because of the increased molecular activity or increased molecular mobility. The molecular attraction is weakened because of the spacing between the molecules increases. Therefore, the cohesive forces is broken, it gets weakened, and hence what happens, the surface tension gets decreased. So with increase in temperature, the surface tension decreases. This is one aspect. With the increase in temperature, the surface tension decreases. Okay. And also the other factor which affects surface tension is, it is also dependent on the fluid in contact with the free surface of liquid. Say for example, in the example we discussed when we try to describe the concept of surface tension. So we considered an open container in which water is stored, which has got a free surface. This is water, and here you have air, that is atmosphere. So water is in contact with air. Suppose instead of air, suppose you have some other lighter liquid, say for example oil or kerosene for example, which has got a density lesser than that of water. So now here water is in contact with kerosene, so the surface tension will be different. So water in contact with air, the surface tension is different. So surface tension is dependent on the fluid which is in contact with the free surface of liquid. Now if you take water, the surface tension for water coated in contact with air, it varies from 0.0736 Newton per meter at this temperature. So we have seen that temperature affects the value of surface tension. The nature of fluid in contact with the liquid affects the surface tension, to 0.0589 Newton per meter at 100 degrees centigrade. So with increase in temperature, the surface tension decreases. So at 90 degrees centigrade, the surface tension of water in contact with air is 0.0736 Newton per meter, whereas at a higher temperature, that is 100 degrees centigrade, boiling point of water, the surface tension is reduced from 0.0736 Newton per meter to 0.0589 Newton per meter. So these values show the decrease in magnitude of surface tension with increase in temperature. If you take the organic liquids, many organic liquids in contact with the air, they have values of surface tension ranging between 0.026 Newton per meter and 0.0304 Newton per meter. If you take mercury, which is which has got a very high density, has a value of 0.4944 Newton per meter at normal temperature, with fluid in contact with mercury being air. So this is an objective MCQ question. So surface tension of water increases with decrease in temperature, decreases with decrease in temperature, independent of temperature, none of the above. So we see that when the temperature increases, the surface tension decreases. So what it is given, when the temperature decreases, the surface tension increases. So this is the correct answer. Decreases with decrease in temperature? Not. It is when the temperature increases, surface tension decreases. When the temperature decreases, surface tension increases. So you have got an inverse relationship between temperature and surface tension. So decreases with decreased temperature, wrong answer. Independent of temperature, it is dependent on temperature, so wrong, none of the above. So the correct answer, the correct option is increases with decrease in temperature. Now let us illustrate the effect of surface tension on a liquid droplet. So if you take, what is a droplet? So if you consider a liquid droplet which gets initially separated from a surface of main body of liquid. So for example, if you take, say rain occurs, it falls on the roof surface and then it goes down and then it is falling down, right, in the form of droplets from the beam or whatever it is, right, the roof ridges. It is due to the surface tension. So what is the shape that is ultimately acquired? It is a spherical shape. So when the droplet forms and which gets separated from the main body of the liquid, ultimately it gets the shape of a sphere. So if you consider the shape of the droplet, which is a sphere, so droplet shape is spherical. Shape of droplet of liquid is spherical. Now when it is getting when it is getting separated from the main body of liquid, it gets contracted to the form of a sphere. So how it is getting contracted? So when it is getting contracted in the sphere, you have external pressure, that is as well as internal pressure within the droplet. So the internal pressure, what happens when it is getting contracted to the form of a sphere, the internal pressure increases within the droplet. The internal pressure increases within the droplet. So how far the contraction of droplet continues? That is, the contraction is a reduction in size, continues till the force due to surface tension, which is acting on the surface of the spherical droplet, is in balance with the internal pressure. So please note how a liquid droplet is formed. A liquid droplet is formed from the main body of liquid. So in fact, the liquid droplet gets initially separated from the main body of liquid. Due to surface tension, there is a net inward force over the entire surface of the droplet. Net inward force over the entire, this is the net inward force over the entire surface of the droplet. And due to this net inward force, what happens? The internal pressure increases. See, I have a droplet which is getting separated from the main body. It is getting contracted. When it is getting contracted, I have net inward force due to surface tension. net inward force due to surface tension. So when it is getting contracted, the internal, so here you have the liquid molecules, the internal pressure increases. So the internal pressure will act in a direction opposite to the direction of the net inward force that is due to surface tension. So how long the contraction continues? Till the force due to surface tension is in balance with the internal pressure. That is the equilibrium condition. Under such equilibrium condition, the droplet attains a spherical shape. So that is the shape which has got the minimum surface area. So when the droplet is in equilibrium, that is when it attains a spherical shape which has the minimum surface area, the force due to surface tension balances the force due to internal pressure. So what is the force due to surface tension? Let us consider spherical droplet of radius r. The net inward force that is acting, there is, in fact, you can put the inward force like this. This is sigma. Thereby the internal pressure will increase. The internal pressure, suppose if you have a cut section, that is, you divide this sphere into two hemispheres, and two hemispheres, this is one hemisphere and this is another hemisphere, and here the internal pressure will be acting normal to this section, internal pressure. So pressure, it is a stress quantity. So what is the area over which this pressure, internal pressure, acts? Whereas surface tension is it is per unit length. So surface tension is the force required to keep unit length of the liquid film at the free surface in equilibrium. So it is Newton per meter. Sigma is in Newton per meter. Sigma is Newton per meter. P is Newton per meter square. It is a stress quantity. So what is the area over which the internal pressure is distributed? So how will you get? So if r is the radius of the sphere, then pi r square is the area over which P acts. And sigma, it acts over a length pi r, that is circumference of the droplet. So sigma acts over a length pi r, the circumference of the droplet. So when the droplet is in equilibrium, that is when it attains a spherical shape which has got the minimum surface area, these two forces should balance. That is sigma into pi r will be balanced by P multiplied by pi r square. That is this one. Sorry, 2 pi r. I'm sorry. Circumference is 2 pi r. I'm sorry. 2 pi r. Or if you use the diameter, it will be pi d. So circumference is pi r, 2 pi r. So sigma multiplied by 2 pi r will be balanced by P into the area over which P is distributed. That is pi r square is the area, the circular area, the section on which P acts normally. So this is the equation when the droplet is in equilibrium. So sigma, that is Newton per meter, multiplied by the circumference of the droplet, that is 2 pi r. So you get Newton per meter multiplied by meter is equal to P is in Newton per meter square into the area is meter square, pi r square. So meter square and meter square get cancelled, meter and meter gets cancelled, so Newton equal to Newton. So you can find out P, that is the pressure in excess of the external pressure. What is pressure in excess of the external pressure? The external pressure is what atmospheric pressure is acting. Here you have to say atmospheric pressure. So atmospheric pressure is acting on the droplet. So this P is the pressure in excess, that is the internal pressure that is in excess of the external pressure. The internal pressure or the inside pressure, the pressure inside the droplet which is in excess of the external pressure. The external pressure is atmospheric. So the pressure inside is above atmospheric. So we are finding out only that excess portion, that is P is equal to, if you simplify you will get 2 sigma by r. So this equation indicates that the internal pressure intensity increases, the internal pressure intensity increases with decrease in size of the droplet. That is, P is inversely proportional to the radius of the droplet. Instead of R, if you want to use the diameter, you can use the diameter also. So again, I am summarizing. At equilibrium of the spherical droplet, the force due to surface tension is balanced by the force due to internal pressure. You are considering a spherical liquid droplet of radius r having internal pressure intensity P in excess of the outside pressure intensity. That is, we assume the liquid droplet to be present in the atmosphere. The outside pressure intensity is equal to atmospheric pressure. Now, if the droplet is cut into two equal halves, then the forces acting on one half of the droplet will be internal pressure intensity on the projected area pi r square, P acts perpendicular to the projected area, tensile force due to surface tension acting around the circumference 2 pi r. Okay. Next one. Let us illustrate the effect of surface tension considering a liquid jet, that is pressure intensity inside a liquid jet. So a liquid jet of radius r, it is a circular liquid jet of radius r, length L, length is L, radius is r, internal pressure P in excess of outside pressure intensity. If the jet is cut into two halves along the length of the jet, so you are cutting here, into two equal halves, then what is it you will get if you see from the bottom? If you cut along the length, what you will see from the bottom is a rectangle. Such that this is L and this is 2r, the diameter of the jet. In terms of radius, it is 2r. So what is the internal pressure intensity P? P acts normal to the projected area. The projected area is the area of this rectangle, that is 2r into L. So P into 2r into L. So this will be balanced by the force due to surface tension. Where the surface tension acts? The surface tension acts on this length as well as on this length. The surface tension acts in this direction. So sigma into L plus sigma into L. So this becomes 2 sigma L. So the force due to surface tension is 2 sigma L, and the force due to internal pressure intensity is P multiplied by 2RL, and these two should be balancing with each other. So sigma into 2L is equal to P into 2RL. So you get P is equal to sigma by R. So for equilibrium of the liquid jet, circular liquid jet of radius R and length L, the force due to surface tension must be equal and opposite of the force due to internal pressure intensity. Now let us illustrate the effect of surface tension in a soap bubble. Now what is a soap bubble? What is the difference between a soap bubble and a liquid droplet? So liquid droplet, you have outside, say it is air, inside you have liquid molecules. Whereas in a soap bubble, you have air outside as well as air inside. For instance, a soap bubble floating in atmosphere. Now, there will be a net inward force because of the liquid surface in contact with the air outside, and there will be a net upward force also due to the air inside. So in fact, a soap bubble has got outer surface and inner surface in contact with the air. Therefore, both outer and inner liquid surface of the soap bubble are subjected to surface tension of same magnitude. So radius is R. So the internal pressure P in excess of outside pressure intensity. So you have P into pi R square will be 2 sigma into 2 pi R. So you have net inward force on either side. Net inward force on either side, that is above as well as inside. Outer outside of the soap bubble and inside of the soap bubble. You have two surface tensions. So force due to surface tension acting on both outer and inner circumference of the projected area on one half of the bubble, So we can equate 2 sigma 2 pi r is equal to P into pi r square. So P, you get 4 sigma by r. So next we move on to capillarity. Is an associated property of surface tension. Suppose if molecules of certain liquid have greater affinity for solid molecules than the attraction between molecules of the concerned liquid, or in other words, the liquid has greater adhesion than cohesion. That is, adhesion is greater than cohesion for the particular liquid. The property of adhesion is more than the property of cohesion for the particular liquid. Then what will happen? The liquid will wet the solid surface, with which it comes in contact, and as adhesion is more than cohesion, the liquid will tend to rise at the point of contact. So the liquid surface becomes concave upward and the angle of contact theta is less than 90 degrees. Say for example, let me open a blank slate. So for example, you consider a beaker in which, say for example, I have a liquid with a free surface. Now insert a small tube, a capillary tube of diameter or radius r. Now what happens here? The liquid will rise to a certain height. Let me blow up this particular portion inside the tube. So the tube is like this, say. This is the free surface of liquid in the beaker. And here what happens? The liquid rises above the general surface and then it attains a shape like this. This meniscus, the meniscus of the liquid surface inside the capillary tube is concave, upward. See, you talk about cohesion as well as adhesion. So this liquid has got more affinity towards the solid surface with which it comes in contact than the intermolecular attraction. Therefore, what happens? Because the attraction is more for the foreign molecules, there is a rise of liquid towards the wall. And the surface of liquid at the center is depressed because the intermolecular attraction here is less. Adhesion is more. This is because of adhesion, and here it is because of cohesion. So adhesion is dominant than cohesion. Adhesion is predominant. So it wets the solid surface and rises at the point of contact, and this angle, this is what we call the angle of contact. This angle of contact is less than 90 degrees when you have adhesion greater than cohesion. Okay. So we are considering a glass tube of small diameter which is partially immersed in water present in a container. Water wets the surface of glass tube and it rises in the tube to some height above the normal level of water surface in the container. The angle of contact, for example, water with glass, it is 0. If it is water, right, this is the normal level of say normal water surface. This is your capillary tube. So what happens here, the meniscus is like this. That is, here the angle of contact theta, in fact the meniscus is tangential to the wall of the capillary tube. That is, theta is equal to 0. Theta is equal to 0 for water in contact with glass. Water in contact with glass. Theta is 0. So let us analyze how the rise of liquid takes place inside the glass when a liquid wets the solid boundary. Why? So I told adhesion is more than cohesion. Now what happens? It results in a decrease of pressure energy within the liquid. There is a decrease of pressure energy. As the liquid molecules wet the solid surface, it is losing some of its energy. That means the pressure energy is lost. So, and therefore, the liquid rises in the glass tube such that the pressure of liquid within the glass column at the elevation of the surrounding liquid surface is the same as the pressure at this elevation outside the glass column. Say, how far it will rise? Say, this is the free surface. Say, this is water. This is free surface. Free surface of water in the container, the big container or the beaker, in which we have inserted a glass tube, that is a capillary tube. So once you insert a capillary tube, the water rises to a certain height as adhesion is more than cohesion. So how far this will rise? Say this is the capillary rise. So how far the capillary rise will occur inside the glass tube. So what happens as the liquid molecules have greater affinity towards the solid surface, it is losing some of its energy. That means pressure energy. So what is the pressure prevailing here? This is free surface, as I told. That is P atmospheric here. The pressure is atmospheric. So you will see that in the pressure of liquid at any point in a horizontal plane is the same. There is no variation. Suppose if you take a XY plane, a horizontal plane, if you take any point, an imaginary plane, let us consider an imaginary plane on the free surface. So here the pressure will be only atmospheric. So what happens? It rises. So when it is rising up, the pressure decreases. So here, so how far it will rise? Till the pressure at this point, that is at any point inside the glass tube at the same level as that of the free surface in the container. When the pressure here is the same as outside pressure. What is the pressure outside? Atmospheric pressure. That is a free surface. So any point in the liquid here, the pressure should be atmospheric. And here the pressure is less than, any point above this, the pressure is less than atmospheric. So this will rise till such a point that the pressure is the same as at this level the pressure is same as the pressure at the outside pressure, that is atmospheric. So it results in a decrease of pressure energy within the liquid. The liquid rises in the glass tube such that the pressure of liquid within the glass column at the elevation of the surrounding liquid surface is the same as the pressure at this elevation outside the glass column. On the other hand, if the molecules of certain liquid possess relatively lesser attraction for solid molecules than intermolecular attraction. Suppose if adhesion is less than cohesion or cohesion is greater than adhesion, say for certain liquids, if the intermolecular attraction is dominant and the attraction it shows for the foreign molecules or the solid molecules is less, in that case what happens? Liquid has greater cohesion than adhesion. then the liquid will not wet the solid surface because adhesion is very, very weak, or it has no adhesion. That when it comes in contact with the liquid surface, it will tend to fall at the point of contact. Instead of capillary rise, there will be capillary fall. So let me describe this in the form of a sketch. Let me open a new white screen. Say for example, I have in an open container mercury. I insert a glass tube, a capillary tube. So I have mercury here. So when I am inserting here, what happens? There is a depression. In fact, when I insert, the mercury level inside the glass tube goes down by this much height. It goes down, the liquid level goes down by a height h. It goes down. So why it goes down? Here adhesion is much more than cohesion. In fact, mercury has no affinity towards glass. It will not, mercury molecules will not stick to the glass surface when it comes in contact, because they have a very strong cohesion. Cohesion is predominant than adhesion. So in such case, there is a fall. Instead of capillary rise, there is a capillary fall, which we call capillary depression. Capillary depression. H is the capillary depression. So that means the level of mercury inside the glass tube goes down by a depth equal to h compared to the general level of mercury in the beaker. There is a free surface of mercury in the beaker. So why? If the molecules of certain liquid possesses relatively lesser attraction for solid molecules than intermolecular attraction, that is, adhesion is less than cohesion, or in other words, liquid has greater cohesion than adhesion, then the liquid will not wet the solid surface with which it comes in contact, and the liquid surface will tend to fall at the point of contact, and the liquid surface is concave downward. Concave downward. In fact, it becomes like this. The meniscus becomes like this. When it is, when adhesion is greater than cohesion, you have concave downward. When adhesion is less than, when adhesion is less than, adhesion is greater than cohesion, this is like when adhesion is greater than cohesion, you have concave downward meniscus. When adhesion is less than cohesion, or cohesion is much more than adhesion, then you have a meniscus like this, that is convex upward, and there is a fall, capillary fall from the general liquid surface. This is the general surface of liquid, normal liquid surface, and this is your capillary fall. H is your capillary fall. And the angle of contact, that is angle of contact, how it is convex meniscus, there is angle of contact. This is the angle of contact, theta, which is greater than 90 degrees, greater than 90 degrees. So you should consider the surface tension also. Now for example, that's what we have already discussed. If a glass tube of small diameter is partially immersed in a vessel containing mercury, as mercury does not wet the glass surface with which it comes in contact, that is, the adhesion is not there, the level of mercury inside the glass tube will be lower than the adjacent mercury level in the vessel with an angle of contact theta equal to or about 130 degrees. It is more than 90 degrees. So let us now discuss why the mercury falls. How far the mercury will fall inside the glass tube, which is partially dipped in the container with mercury. So it is not adhering to the solid surface. Adhesion is not there. Cohesion is dominant. What happens? It results in creating, in the previous case when water was in contact with glass surface, there was decrease in pressure. Now here it is resulting in increase in pressure across the liquid surface, and because of this increased internal pressure, the elevation of the meniscus in the glass tube is lower to the level where the pressure is same as that in the surrounding liquid. The same concept. So till what level? So that now, say for example, again we'll go back, open this is the capillary tube, beaker containing mercury, this mercury, there is a fall. So what is the pressure here? This is the free surface, that is P atmospheric. Now the pressure at any point here inside the beaker, so this will be, let be P. P is greater than P atmospheric. In fact, P is equal to P atmospheric plus specific gravity of mercury into H. H is the capillary, this depth is H. So this will be studied in fluid pressure and its measurement in the next chapter. So P atmospheric plus gamma m is the specific weight of mercury. Specific weight of mercury. Specific weight of mercury. H is the capillary fall. So this will go down till such a point. What is the pressure here at the meniscus? The pressure at the meniscus is the same as the pressure here. What is the pressure here? That is P atmospheric plus gamma m into H. So because of the increase in pressure, So as mercury does not adhere to the solid surface, it results in creating an increase in pressure across the liquid surface, and because of this increased internal pressure, the elevation of the meniscus in the glass tube is lower to the level where the pressure is the same as that in the surrounding liquid. Now let us define the term capillarity. It is defined as the phenomenon of rise or fall of a liquid surface related to the adjacent general level of liquid. This rise of liquid surface related to the adjacent general level of liquid is known as capillary rise. Is known as capillary rise. Is known as capillary rise. Whereas the fall of liquid surface related to the adjacent general level of liquid surface is known as capillary depression, as in case of mercury. So what is the SI units? It is nothing but capillary rise or depression is nothing but a column, a vertical rise or a vertical fall of liquid. So it is only meters or millimeters of liquid. Meters or millimeters of liquid. So we are using millimeters because the length involved, the fall or the rise involved is very less, is very meager. So we can use millimeters. So we can express conveniently. Okay. So this gives the derivation of expression for capillary rise or capillary depression. So you have to again consider, as in surface tension we consider the equilibrium of the spherical droplet, how the forces are balanced. Here we have to consider the equilibrium of conditions of equilibrium of a circular glass tube of small diameter inserted in a liquid and let the level of liquid in the glass tube has risen or fallen by h above or below the general level of liquid surface in the container in which the glass tube of radius r is partially inserted. So this is what? This is capillary rise, this is capillary depression. So here the level of liquid has gone up inside the glass tube related to the general level such that the pressure here inside the glass tube is the same as the pressure here, that is atmospheric. Whereas here the pressure here is the same as the pressure at this level, that is in excess of atmospheric pressure, more than atmospheric pressure here because of the increase in pressure. Here there is a decrease in pressure involved in capillary rise. So what are the forces acting on the mass of liquid above, lying above or below the general level of liquid surface in the container? Now let us take this, the equilibrium of this portion. The rise of liquid. So the weight of the liquid column H in case of capillary rise or the total internal pressure in case of capillary depression. So if it is a capillary rise, we have to consider the weight of liquid in the column H. In the column H. If it is capillary depression, we have to consider the total internal pressure in case of capillary depression. Then force due to surface tension at the surface of the liquid in the glass tube. So we have to balance these two forces. The algebraic sum of vertical forces acting on the mass of liquid column H must be equal to 0 for static equilibrium of the column of liquid above the general level of liquid surface. The algebraic sum of vertical forces acting on the mass of liquid column must be equal to 0. There are only two forces. There are only two forces, 1 and 2. In case of capillary rise, the weight of the liquid column H acting in the vertical downward direction must be balanced by the upward vertical component of the surface tension of liquid. So what is weight of liquid column? Weight of liquid column is volume of the liquid column H multiplied by specific weight of liquid. So volume of liquid column is, it's a cylindrical column, so pi r squared is the area multiplied by H will give you the volume of liquid column H. Volume of liquid column H. Specific weight is gamma, so you get the weight of a liquid column. Then vertical upward component due to surface tension is component of sigma in vertical upward direction. So sigma acts here. So what is the component? That is sigma cos theta. Sigma cos theta is the component of sigma in vertical upward direction. So this is weight of liquid column is vertical downward. This is, I want the upward component due to surface tension. So component of sigma in vertical upward direction is sigma cos theta. So it is a linear force. So it acts on the circumference of the glass tube, that is 2 pi r. So these two must be balanced. These two forces must be balanced. So equate pi r square H multiplied by gamma is equal to sigma cos theta multiplied by 2 pi r. So you get capillary rise as 2 sigma H is equal to sigma cos theta by gamma r. So MCQ, the rise of liquid or specific weight gamma in a capillary tube of radius r is given by, just you have to pick out the correct expression. So the correct expression is 2 sigma cos theta by gamma r. So C is the correct option. So examine the following 4 statements. Another MCQ. Surface tension is due to cohesion only. Capillarity is due to cohesion only. Surface tension is due to both cohesion and adhesion. Capillarity is due to both cohesion and adhesion. See, surface tension is only due to cohesion. Capillarity is due to both cohesion and adhesion. Both cohesion and adhesion. Capillarity, so this is wrong. This is wrong. Surface tension is only due to cohesion, whereas capillarity is due to both cohesion and adhesion. So the correct answer is 1 and 4. So We have some examples, and I think these examples we will discuss in the next module on surface tension and capillarity, and also I will try to work out a few problems given in some competitive examinations like GATE or Indian Engineering Service. So with that, thank you for the day. Thank you.